you for being patient. The last example I did with my earlier class went significantly over time, not really leaving me enough time to go use the bathroom between. So something had to give. Again, I appreciate your patience. Today we're going to dive into trig sub. Since we are a little crunched for time, I'm just going to get right away started with this. Cam. Get into it. I did notice just signing in here that I never linked in the announcements to the recorded lecture from last week. So I have that uploading right now, and I'm going to link that immediately after class today. So if you wanted to go back and review last Friday's lecture, it will be up in just a few minutes after class. But today is all about section 7.3 on trig sub. And we did a pretty good job talking about and motivating this last week. So I'm trusting that you guys were able to follow that and think about that stuff a little bit. I'll give a brief introduction and motivation, but then we're just going to get into examples because really, like with everything, the best way to learn this is to practice it. I'll remind you, our basic motivation is that square roots loathe, that is, they hate addition and subtraction. And what I mean by that is like the square root of x squared minus 1 is very much not x minus 1. The square root of x squared plus 1 is very much not x plus 1, and the square root of 1 minus x squared is certainly not 1 minus x. So please don't ever try to simplify any of those things or similar things according to the rules that appear to be going on here. This shit just doesn't work. If you're uncertain, plug in a few numbers, right? If I plug in 0 here, then I should get the square root of -1, which would be I. If I plug in 0 here, I get -1, and I and -1 are not the same. If I plug in 1 here, I get the square root of 2, which is irrational and definitely not equal to the rational number 2. So this shit just doesn't work. The thing I want to share with you next is what I call my trig sub Bible. So look at this guy. If x was sine theta, then this would be 1 minus sine squared theta. Oh, well, that's cosine squared. So then this would be the square root of cosine squared theta. That's just cosine theta. So here's how it goes. If your integral has, and then I'm going to have 3 different things here, then substitute, and I'll put the substitution here, because, and I'll put a brief explanation over here. Now throughout all of this, u, I'm going to use the symbol u, is understood to be a function of x, but usually linear. So if your integral has something that looks like the square root of some constant squared minus some linear function of x all squared, and I wrote it like that again. Some linear function of x all squared, there's nothing here. Then you should substitute u equals a sine theta. Why? Because the square root of a squared minus a squared sine squared theta is going to simplify to the square root of a squared cos squared theta, which is just a cos theta. And I'll show you the mechanics for this. You factor out the a squared, then 1 minus sine squared is cos squared. On the other hand, if your integral has a square root of a squared plus u squared, then you should substitute u equals a times the tangent of theta, because the square root of a squared plus a squared tan squared theta, which is what you get when you make that substitution, simplifies to the square root of a squared secant squared theta, which is just a times secant theta. And then finally, if your integral contains something that looks like u squared minus a squared, where u is a linear function of x, then you should substitute u equals secant theta, a times secant theta, rather. Because then your square root will become a squared secant squared minus a squared. And if you factor the a squared, you'll see that that's secant squared minus 1. So that'll be the same as the square root of a squared tan squared theta, which is a tan theta. Okay, this you need to know. You got to remember this. You got to at least remember this part of it. This stuff you'll be able to figure out through the course of solving the problem, but you must remember this part. So if your integral has something like this, you substitute something like that. You got to remember that. Okay, there are no formula sheets on the test. I won't be giving you this on the test. You have to remember it. You solve enough problems, you'll remember it, right? That's all. That's all. So by going through the homework and solving the homework honestly by yourself, working through it and struggling with it a little bit, you will remember this. One trick for remembering this is, like, think about the special case where a is 1 and u is x. Then this is 1 minus x squared. So what Pythagorean identity looks like 1 minus your trig function squared? Oh, that's the 1 minus sine squared identity, right? 1 minus sine squared is cos squared. The same is true for this. If this was 1 plus x squared, which trig identity kind of looks like that? Oh, well, 1 plus tan squared, that's secant squared. And then finally here, which trig identity looks like my trig function squared minus 1? Well, that's secant squared minus 1. That's the identity. So by thinking about the appropriate trig identity, you can remember the substitutions. But most people commit this portion of the table to memory. And again, it'll get in there just by solving problems. But if you're having a hard time remembering which substitution to make, you might consider making some flashcards for these before the test. It all depends on where you land after practicing the homework. But do the homework first. I suspect you'll remember it, no problem. Okay, so let's solve some problems. We did one problem, one or two problems last week. And I don't want to go back through those same problems, but I do want to practice with some slightly more challenging ones today. So if you look at this guy, which one of these three square root type things does this look like?
The first one?
Yeah. This is a constant squared minus my variable squared. Well, this is 3 squared minus x squared. So here I should substitute x equals 3 times the sine of theta. So a here is 3. And then dx, that would just be 3 cos theta d theta. And the good news with trig sub, it's kind of a backward substitution, right? Instead of saying like z equals 5 minus x squared, you have x equals something involving theta. So you can just plug this in for dx. You don't have to find the appropriate piece to substitute for. You don't have to find dx or your differential floating around in here somewhere. You just plug it in. So in place of dx, I'm going to write 3 cos theta d theta. So if I go plugging all this in, the x squared upstairs, that's 3 sine theta squared. The square root piece downstairs is going to be the square root of 9 minus 3 sine theta all squared. And then dx is 3 cos theta d theta. And now I'm going to start simplifying. This is 9 sine squared theta times 3 cos theta from my differential all over the square root of 9 minus 9 sine squared theta d theta. And in this square root downstairs here, I can factor a 9. Upstairs, 9 times 3 is 27. We've got sine squared times cosine. And downstairs here, I've got the square root of 9 times parentheses 1 minus sine squared theta, all under my square root. And then this 1 minus sine squared, that's cos squared. So this will be integral 27 sine squared times cos all over the square root of 9 cos squared theta d theta. And the magic is that here, and in my original, I had some subtraction going on under the square root, but now down here, I don't. So I can't take the square root of the 9 and the x squared separately because they're being subtracted, but here I can take the square root of the 9 and the cosine squared separately because they're being multiplied. They're a single term. So I'll have 27 sine squared theta times cos theta divided by the square root of 9 is 3 times the square root of cos squared is cos. And the cosines cancel. 27 over 3 is 9. And what's left is just the integral of sine squared theta. Neat, right? Once you get to a place like this, you've reduced it to a 7.2 problem. You've reduced it to a problem of the sort we were doing in the homework last week. How do you integrate sine squared? How do I do this integral? Good. It's a half angle identity, right? It's a sine cosine integral where the powers are all even. So I pop out the 1/2, that turns my 9 into a 9/2, and then I'll have 1 minus the cosine of 2 theta. It's perfect. D theta. Yeah, good job, Brian. And then from here, my antiderivative step is not hard. This is 9/2 times theta minus sine 2 theta over 2 plus c. Okay. If the problem was given to me in terms of the variable theta, I would be happy with this answer and I would say stop here. But that's not the case. This problem was given to me in terms of the variable x. So my answer has to be given in terms of the variable x. So I need some way to go from thetas back to x's. And that's why you'll see I left some space over here. What I'm going to do to go back and forth from this theta expression to x's is I'm going to draw a triangle. So if x is 3 sine theta, then sine theta is x over 3. Do we all agree on that? Just divide both sides by 3. And then I interpret this geometrically using SOHCAHTOA as the opposite over the hypotenuse of a triangle. What triangle? This triangle. The triangle you're going to draw. A right triangle. Where I will label the opposite side as x and the hypotenuse as 3. And then I use the Pythagorean theorem to complete the triangle. So this squared plus this squared equals this squared, which means this has to be the square root of this squared minus this squared. The missing side on your triangle will almost always be the square root expression in your integral. And that's the other piece I always put into my trig sub little substitution box, right? We always have to put our little substitutions in these boxes. And over here, where normally I would put the bounds changing work, if it was a definite integral on indefinite integrals using trig sub, I always draw my triangle here. I'm going to copy that triangle down here so everybody can see what's going on. So you may remember in your trigonometry classes having to write expressions like this. They would say, rewrite this trig expression as an algebraic function of x. There's a reason why. This is why. I also have this theta here. So there's a little bit more work to do. Remember, the substitution we made was x equals 3 sine theta. So first, can anybody tell me what theta is? This is the same as saying sine theta equals x over 3. So what is theta?
The inverse sine of x over 3.
Good. You take the inverse sine of both sides, and you can write it however you want, as this, or you could write it as the ARC, arc sine. Just remember that it's not the same as 1 over sine, right? It's the inverse sine function. This first piece, I could write as the inverse sine of x over 3. That's the theta. And then this piece, I have a triangle for theta, but not for 2 theta. And it's hard to get a triangle for 2 theta right away. So first I should apply the trig identity sine 2 theta equals 2 sine theta cos theta. And then I still have my over 2 here, so the 2's will cancel. So finally I get 9/2 times the inverse sine of x over 3 minus, now sine theta and cos theta I can read off from this triangle. The sine of theta is the opposite over the hypotenuse, that's x over 3, times the cosine of theta is the adjacent over the hypotenuse, that's the square root of 9 minus x squared over 3. And now you're done. You could distribute the 9 halves and simplify a little bit, but this is the important skill. Right, is that you can go back from your trig stuff to your X algebra stuff. I know that this procedure might be a little bit frightening because trigonometry at Santa Fe kind of sucks. I taught one semester of trig here and I was shocked, to be honest, at how bad the book is, how bad the curriculum is, and frankly, how weak the class is in general. It's not good, it needs to come up. And maybe it didn't bite you in the ass in Calc 1. Maybe your Calc 1 class didn't have a whole lot of trig, but there's no escaping it in Calc 2. You must master the trig. Let's come back a few steps and first take care of any questions on the integration. So putting in that substitution, figuring out how everything simplifies. So questions up to here, questions on any of this stuff. Do we see where all these pieces are coming from? X squared, well, if x is 3 sine theta, then that's 3 sine theta all squared. Same thing down here, 3 sine theta all squared is x squared. And dx, I just plug in. dx is 3 cos theta d theta.
And you got those numbers from where?
So,
The x and the dx.
so I chose to make the substitution x equals 3 sine theta, following my trig sub Bible. So my square root in my integral, where can I get these things both to show up in the same bit? The square root in my integral is 9 minus x squared, right?
Correct.
A squared minus u squared, a must be 3 because a squared is 9, and u must be x because u squared is x squared. So according to my little trig sub Bible, I should substitute u equals 3 sine theta.
Got it. Thank you.
Okay, what else?
I'm getting lost where we do like the, hold on one second.
Sure.
Everything after the half angle identity.
So you're comfortable up to the half angle identity?
Yes.
So from here, I know that sine squared theta is 1/2 1 minus cos 2 theta. This is one of those identities we used a lot in our homework last week. So I'm taking this sine squared theta and I'm replacing it by 1/2 cos 2 theta. That's here. Here's the 1 minus cos 2 theta. And I popped out the 1/2. That turned the 9 into a 9 halves. Are we comfy with that?
Yes.
Okay. And then the antiderivative step here isn't bad. 1 d theta will integrate to theta. Cos 2 theta, that's a micro u sub. He'll integrate to sine 2 theta over 2. And I slap on my plus c here. And then I use the double angle identity for sine. Sine 2 theta is 2 sine theta cos theta. to rewrite sine 2 theta over 2 as 2 sine theta cos theta over 2, and I canceled the 2's. So from there, I need to go back to my original variable. My original variable was x. So this theta, I have to take my substitution and solve it for theta. So I divide both sides by 3, and I get x over 3 equals sine theta. And then I took the inverse sine of both sides to get theta alone.
How do you know where to place like the x and the 3 and then?
You could write it on either side. It doesn't matter. I just chose to write the sine theta on the left. But yeah, you could write x over 3 equals sine theta instead. That would be fine.
Okay, because I was getting confused when you drew it out because I don't understand that portion.
Confused about the triangle or about this step?
The triangle and then everything that follows that, because could you like,
So think
if I wrote the x as a hypotenuse instead, then it would be considered wrong.
it absolutely would be, yeah. So this is coming from SOHCAHTOA. Remember this from trig? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So once I have sine theta equals x over 3, I go, okay, well, according to SOHCAHTOA, this has to be my opposite, and this has to be my hypotenuse. So sine theta is always opposite over hypotenuse, and in this case, sine theta is x over 3. So x has to be my opposite, and 3 has to be my hypotenuse.
Okay.
And then from there, I use a squared plus b squared equals c squared to solve for the missing side.
Okay. That makes sense.
It's crazy how everything comes together. That's insane.
Yeah, I mean, that's good instructional design, right? That's because the courses are designed to flow together. It's not a coincidence that these things come together.
No, yeah, for sure. Yeah, I agree.
But okay, so if we're comfy with where the triangle comes from, and we're comfy getting to here, are there any questions about why theta is the inverse sine of x over 3? Are we okay with that? Going from here to here?
You just solved for theta.
Yeah. Yeah, the way I get rid of a trig function is by applying the inverse of that trig function to both sides. So kind of inverse sine is to sine as square root x is to x squared. If I want to get rid of a square, I take the square root. If I want to get rid of the sine, I take the inverse sine. So if I had like theta squared equals x over 3, then theta would be the square root of x over 3. The sine of theta is x over 3 means theta is the inverse sine of x over 3. And then my very last step is to take this simplified form of sine 2 theta, which is 2 sine theta cos theta. And then I look at my triangle. I say, okay, well, what is sine theta? According to my triangle, sine theta is x over 3. Now, what is cos theta? According to my triangle, cos theta, which should be adjacent over hypotenuse, is the square root of 9 minus x squared over 3. So I just plug those in for sine and for cosine, and then we're done. Neat stuff, right?
Wait, I have a question. I don't know why I lost it, but back to the trig. How did you get sine theta equals x over 3?
That's coming from the substitution I started with. So I began by making the substitution x equals 3 sine theta. Divide both sides by 3.
Yeah, that makes sense. Got it. Thank you.
No problem. So kind of everything you need is tucked in here. I like to draw the triangle right away, because then that will kind of remind me when I get to the end, oh yeah, you got to go back to the original variable, and the way you do it is with the triangle. So I do all this in my very first step. And then when I get to the end, if I'm lost or if I'm struggling to remember what to do, I can kind of look at this triangle and go, oh yeah, that's the key to go back and forth between thetas and x's.
Thank you.
Of course. Let's try another indefinite integral. Let's try another one kind of like this. Oh, and I already used this side, so we'll do this. Let me grab this out of your textbook. There's so many things to choose. This is a good one. Oh wait, no, that doesn't require trig sub. This is okay. Right? Yeah, okay. 1 over x squared times the square root of x squared plus 4. So looking at this and thinking about my trig sub Bible, I look just at the square root piece and I ask, which of those things does this look the most like?
The middle one?
Yeah, this is the one with addition, right? Only one of these has addition under the square root. So here I've got like a squared plus x squared, right? Or x squared plus a squared. The order there doesn't matter because addition is commutative. So I should substitute what? X equals something involving tangent, right?
Yeah.
This is a.
4 tangent of theta.
Not quite. So remember, this isn't a itself. This is a squared.
Oh, 2 tangent of theta. Sorry.
Yeah, very good. That's perfect. So then dx will be 2 secant squared theta d theta. Oops, sorry, that's camera. Okay, and then also while I'm here, I'm going to draw my triangle. So this is the same as saying tan theta equals x over 2. So this is the opposite, and this is the adjacent. Sorry, that looks like a DDJ, adjacent, right? Tangent from SOHCAHTOA is opposite over adjacent. So my opposite side is x, and my adjacent side is 2. And then this side, you know that this squared plus this squared equals this squared. So this is the square root of this squared plus this squared. So this is the square root of 4 plus x squared. So there's my little substitution box. One dx, that's 2 secant squared theta d theta. And I'll put the secant squared stuff upstairs. X squared is 2 tan theta squared. And my square root is 2 tan theta squared plus 4. My 2 secant squared theta from the differential is upstairs there, so I just need to put my d theta over here. Everybody comfy with how we go from here to here? Okay, so then I've got 2 secant squared theta. Downstairs there, I've got 2 tan squared theta. Oh, sorry, 2 squared tan squared theta. Or 4 tan squared theta. I'll write it like this for now. And then under my square root, I've got 4 tan squared theta plus 4. So this, I wrote a 2 before I thought to write the square. So it's 4 tan squared theta. We'll write it like that for now. So this is integral 2 secant squared theta over 4 tan squared theta. And then in here, I'm going to factor out a 4. So I keep it in the square root 4 times tan squared theta plus 1. Like that. And that's the magic, right? Is that this becomes this, and tan squared theta plus 1, according to your second Pythagorean identity, is secant squared theta. So this will be, I'm going to go ahead and cancel the 2 and the 4 here. So this will be secant squared theta over 2 tan squared theta times the square root of 4 secant squared theta. Because this piece here is secant squared theta. We're using the identity there. Tan squared theta plus 1 is secant squared theta. Now I can take the square root of this stuff because there's no more addition or subtraction. It's just multiplication. So that's integral secant squared theta over 2 tan squared theta times the square root of 4 is 2. The square root of secant squared is secant. And you can cancel one of the secants. So you get secant, just regular secant theta over 2 tan, let's see, what do we have downstairs? I've got another 2 down here, so we'll call that 4 tan squared. So I can pop out the 1/4. I always wait to pop out my constants until I've simplified all of them, and then I just have secant theta over tan squared theta d theta. And now it's a 7.2 problem. So how do we do this trig integral?
U sub? No.
Maybe. I don't see anything to substitute for right away though, right? If it was secant times tangent squared or something like that, if they were both upstairs, then I would be in a position to start considering u sub. So maybe first I should rewrite in terms of sines and cosines.
Okay.
So in order to be efficient with my paper, I might do a little bit of this and a little bit of this and continue it over here. So that's 1/4. Having a secant upstairs is having 1 over cos theta. And then tan squared downstairs, that's cos squared theta over sine squared theta, like this, right? I'm dividing by tan squared. Tan squared is sine squared over cos squared. So I'm dividing by that. That's the same as multiplying by its reciprocal. So this piece is secant. This piece is the reciprocal of tan squared. I can cancel a cosine. And I get cos theta over sine squared theta d theta. And now, yeah, you sub. What do I sub for?
Sine.
Yeah,
Would
just sine. Yep. Because I've got the cosine upstairs that I need to substitute for the sine downstairs. So this will become 1/4 integral 1 over z squared. Which I can think of as 1/4 integral z to the negative 2. Which will integrate to 1/4 negative 1/4. I'll write it like this: 1/4 times negative 1 over z, or z to the negative 1 plus c. And now I need to chase back through two different substitutions. First, I'm going to plug in sine theta for z. So I'll get 1/4 negative 1 over sine theta. But then before I can call it quits, I need to go back to my x's. So what is sine theta? How do I figure that out? Well, I look back up here at my triangle. Sine of theta, so this triangle tells me sine theta is the opposite over the hypotenuse. The opposite angle here is, or the opposite side here is x. And the hypotenuse is the square root of 4 plus x squared. So 1 over sine theta is the reciprocal of that. And that's what I need to plug in down here. So this guy is 1/4 times negative square root 4 plus x squared over x plus c, like that. Neat stuff, yeah? Questions on this guy? Looks like we did get it all here. So I can come back like this, and do not like this. Try to straighten the camera like that. Focus.
Very long problem.
Actually, this is kind of gentle. These get much worse.
So I have to master this now.
Yeah, and one of the things you'll adjust to in this class is the idea of problems taking several pages and that sort of thing. I recommend a whiteboard. I don't know if you can see over here, this whiteboard. This is your friend. This shit, Masonite, like $10, $11 from Home Depot for a 4x8 sheet. You can hang it on your wall with a couple of drywall screws, And then you got all the space you ever need to practice problems. I recommend it. I bought my first whiteboard like that when I was in Calc 2 because it was useful. You go to buy a porcelain whiteboard or an official whiteboard from Amazon or something like that, you're going to pay several $100s for something that size. But you go to Home Depot or Lowe's, look in the section, like the lumber section where they've got little thin masonite covers, find a piece of laminated masonite. Last time I went there, I think it was like $11.95, but it varies. Much, much cheaper than buying a whiteboard. It works great. You can write on it with whiteboard markers. It erases just like a whiteboard, and they're cheap as hell. I strongly recommend it.
Does it only come in those large sheets, or are there smaller options?
They'll cut it down for you. I think it only comes in the 4x8s, but if you ask them to cut it in half or cut it into thirds, they'll do that for you also. So you could get one big sheet and then cut up like a couple little whiteboards to carry around and one medium size to hang on the wall or whatever you want.
Yeah, I might consider that.
Yeah, it's a good move. Questions on any of these steps? Feeling mostly good?
How'd you make it from theta to x again?
So I use my triangle. So once I get to this step where I've got 1 over sine theta, I come back to my triangle and I say, okay, I need 1 over sine theta. So first I figure out what sine theta is. I look at my triangle. Sine theta should be the opposite over the hypotenuse. That's x over the square root of 4 plus x squared. And then I see, okay, well, what I actually need isn't sine theta, it's 1 over sine theta. It's the reciprocal of sine theta. So I take the reciprocal on both sides here. That should be the hypotenuse over the opposite. So 1 over sine theta is the reciprocal of this. It's the square root of 4 plus x squared over x. And that's what I put down here, square root of 4 plus x squared over x. So the triangle is the trick for going back to your x's. Without this triangle, there's nothing doing. But once you have this triangle, you can read off sine theta, cos theta, tan theta, whatever you need, just using the geometry.
Okay, thank you.
Of course. Let's try one more indefinite integral, and then I want to do a definite integral. No, that's a little too tough for us at this stage. X squared over square root of 9 minus x squared. Is this the one we did at the start? I think it is. This is going to be more or less the same. No, shit. What do we want to do? X squared of 1 minus x squared. No, that's too boring. Let's try 29. 29 looking kind of fun. I don't want to scare you guys. Actually, let's do 20. So that's x over 1 plus x squared. That's not too similar to this, is it? No. Okay. No. All right. You know, we haven't done a secant substitution yet, have we? How about x over x squared minus 1? Oh, no, we shouldn't do that. Yeah, I see. Oh, shit. Do we have any good secant sub problems here? Let's do number 9. Oh, that's a definite integral. Okay, we're going to do number 9, but as an indefinite integral. So we'll do integral 1 over x squared minus 1 to the 3/2 dx. So at a glance, this doesn't really look like something from my trig sub Bible. It doesn't have a square root. So you might begin by writing this. You have to think about what that 3/2 power really means. That's the square root of x squared minus 1 cubed. right? That's what a 3/2 power is. It's the 1/2 power cubed, or the square root cubed. So this is how we get started. And then according to my trig sub Bible, I've got the square root of u squared minus a squared. I should substitute x equals secant theta. Because secant squared minus 1 is nice, it's tangent squared. In other words, u here is x and a here is 1. Dx, the derivative of secant, is secant theta, tangent theta, and then my d theta. And also I need to draw my triangle. If x is secant theta, remember secant is the reciprocal of cosine. If cosine is adjacent over hypotenuse, secant has to be hypotenuse over adjacent. So my triangle has to have hypotenuse x and adjacent side length 1. And then if I complete this triangle using a squared plus b squared equals c squared, I'll see that this guy is the square root of x squared minus 1. And again, the missing side of your triangle is almost always the square root from your integral. So there's my little trig sub box with all the good stuff. Questions about where any of this stuff came from so far? All good?
I guess it's the same question as before. Where'd you get the secant from the problem?
So I'm looking at I'm thinking about my trig sub Bible. So the square root of x squared minus 1 looks like which one of these?
Yeah, the second one.
Oh, the second one has a plus.
Wait a minute. Yeah, you're right. Yeah.
It's this guy, right? X squared minus 1. So we have to remember these kind of shapes, the shapes of these square roots. And there, I let u equal a secant theta. So here I'm letting x be 1 times secant theta, because a here is 1.
And how do you know it's not the first one? Because
The order of the subtraction.
the order of the subtraction.
So if it's your variable minus variable squared minus constant squared, if the variable comes first, that's secant. If it's constant squared minus variable squared, that's sine.
Got it.
So
Okay.
like 1 minus x squared, then I would sub sine, but since it's x squared minus 1, I sub secant.
So the u is for like the variable.
Yeah, u is your
Hence, yeah.
x.
Cool. Beautiful. Thank you.
I'll show you an example where this is not just x in a minute. I'm just trying to start with simple stuff. Okay, so that tells me to substitute x equals 1 times secant theta, and then I calculate my differential and I draw my triangle. Now we plug in. So dx is secant theta, tangent theta, d theta. And then downstairs here, I'll have parentheses, square root, secant squared theta minus 1 cubed. Everybody good with that? So if x is secant theta, then x squared is secant squared theta. From here, secant squared theta minus 1 is tan squared. So this is integral secant theta tangent theta over parentheses square root tan squared theta cubed d theta. And the square root of tan squared is tangent, so downstairs this whole mess is tan cubed. So I get integral secant theta tangent theta over tan cubed theta d theta, and I can cancel one of the tangents. So I'll have secant theta upstairs and tan squared downstairs. Oh shit, this looks familiar, doesn't it? Didn't we just do this integral? I think we did. It was coming from a different problem, but it came out to the same trig integral. That's cute. So this is 1 over cosine, that's the secant, times cos squared over sine squared. Cancel a cosine, and you get cos theta over sine squared theta. This is funny, I wasn't expecting this. And then you'll let z be sine theta. So it's the same as the integral we had a second ago. Different x integral, same theta integral. So dz is cos theta d theta. And this becomes the integral of 1 over z squared dz, which is the integral of z to the negative 2 dz, which is negative 1 over z plus a constant, which is negative 1 over sine theta plus a constant. And now I look back to my triangle. The answer here is going to be different than the answer in the previous problem because the relationship between x and theta is definitely different. So here 1 over sine theta, remember sine is the opposite over the hypotenuse. So this will be the hypotenuse over the opposite. So this is x over the square root of x squared minus 1 with a negative plus c. Neat stuff, right? So what we haven't done yet is any definite integration. We haven't done any definite integrals using this method. I would like to do one of those before I let you go. And we were a few minutes late getting started, so I am going to use a few minutes past our official stop time. I'll ask you to be patient and hang out here just for a few extra minutes. First, any questions on this problem? Okay then. So let's grab one definite integral to play with. Why not 14? Why don't we do 12? Let's do 12. I think 12 is better practice here. So that's the integral from 0 to 2, 1 over the square root of 4 plus t squared dt. Again, thinking about my trig sub-Bible, I have a square root of 4 plus t squared here. So I'm going to do a tangent substitution. I'm going to let t equal 2 tangent theta. And dt then is 2 secant squared theta d theta. The difference between this and the indefinite integrals is that here we need to change our bounds. So when t is equal to 0, we'll have 0 equals 2 tangent theta, which means tangent theta is 0 over 2, which is 0. So theta is the inverse tangent of 0, which is 0. On the other hand, when t is equal to 2, you'll have 2 equals 2 tangent theta, which means tangent theta is equal to 1. So theta is the inverse tangent of 1, which is what? What is the inverse tangent of 1?
Pi over 4.
Good, good. Pi over 4. So you got to know your inverse trig stuff, even to get started here, just to change your bounds. So my new integral is going to run from 0 to pi over 4. The 1 dt is 2 secant squared theta d theta. And downstairs, I have the square root of 4 plus t squared, which is 4 tan squared theta. So this is going to be integral 0 to pi over 4, 2 secant squared theta divided by the square root of 4 times 1 plus tan squared theta d theta. And 1 plus tan squared is secant squared, so this is integral 0 to pi over 4, 2 secant squared theta divided by the square root of 2 secant squared theta. And, sorry, square root of 4 secant squared theta. And then the square root of 4 is 2, the square root of secant squared is secant. So you get integral 0 to pi over 4, 2 secant squared theta over 2 secant theta. You can cancel the 2's, you can cancel one of the secants, and you're left with integral 0 to pi over 4 secant theta. Who remembers the integral of secant theta?
Natural log of secant theta plus tangent theta.
Very good. So we'll have natural log absolute value secant theta plus tangent theta. There is no plus c here because this is a definite integral, but we do have to evaluate between bounds. So that's going to be the natural log of the secant of pi over 4 plus the tangent of pi over 4 minus the natural log of the secant of 0 plus the tangent of 0. And again, we need to know what these are. What's the secant of pi over 4?
Two over root 2.
Good, which is just the square root of 2. And the tangent of pi over 4?
1.
Well, you know. The secant of 0 is 1. And the tangent of 0 is 0. So over here we have the natural log of 1, which is 0. And over here we have the natural log of square root 2 plus 1. So this is just this. I'll zoom out a little bit, so if there's something you need to get into your notes, you can. Remember, in this class, you must change your bounds. All right, it's a necessary thing. And if you think about some of the other problems we did where you've got like the trig sub, then a use sub, then maybe something else, if you don't change your bounds as you move through that process, you're gonna have to chase back up through all of those substitutions, then evaluate some big nasty expression between bounds that are potentially themselves kind of nasty. So it's really important that you change your bounds as you go. That will make life much, much easier. I appreciate you guys hanging around a little bit late. Are there any questions on this problem that we'd like to look at before we sign out?
I need to practice. That's all I'm gonna say.
Practice is necessary, yeah. If you get stuck, if you're having a hard time, of course, you can come by my office hours, but remember to also look in the modules. I've got a lot of good review material there. If you're having trouble with the inverse trig stuff, all of those things in the review material modules can help you. And there's also a module there on trig subs, so take a look at that as well. There are some nice videos and things you can watch that will help you with that. Finally, read the textbook, right? The textbook has nice explanations, and because they don't have any time constraints, you know, they can go into a little bit more depth than we did here in class. But work on things, practice, and it will become more natural over time. If you get stuck or you're in trouble, send me an email, come by office hours. I'll do my best to help you out. And that is it. Be mindful, the exam is coming, right? Not this week, but next week. This week we're gonna finish partial fractions, probably Friday, and then we'll be ready for the study guide. So I'll be dropping the study guide this Friday. There will be a new homework coming out today that has some trig sub and a little bit of partial fractions in it. So go ahead and get started on that if you can. It'll be out in about, I don't know, an hour or so, depending on how busy I am in my non-teaching time today. But yeah, that is it. I hope you guys have a lovely rest of your day. Again, the exam, yeah, we talked about this a little bit last week. The exam is going to be, what do we set it for? Next Wednesday, right?
I thought you said it was gonna be next Friday. But I
Next
might be wrong.
Friday? Okay, yeah, Friday is fine. That just means Monday we'll have to cover some new material. So yeah, next Friday, that's cool. Especially if that's what we said last week. So yeah, next Friday, you're right, yeah, because the study guide's gonna drop this Friday. I want you to have a full week on the study guide. So I'll drop the study guide this Friday, and then the exam will be next Friday. That sounds good. I'll write that down so I don't forget. All right. Okay, guys, that is it then. I will see you all either in office hours or on Wednesday.
I had one quick question.
Sure.
What happens at like the second to last step where it says natural log of, yeah, right there.
Natural log of 1 is 0. That's all. So this piece is 0, and the square root of 2 plus 1, that's a positive number. So his absolute value is just him.
Okay.
But yeah, that's all. This piece is 0.
Could you leave it with the absolute value?
You could if you wanted to, yeah. Yeah, there's no harm in leaving this as the absolute value there. But square root of 2 is positive, 1 is positive, so the absolute value of that number is just that number. So either way would be all right.
Okay, thank you.
Alrighty. All right, that sounds good. Come by office hours if you want to talk some more. Otherwise, send me an email or I'll see you on Wednesday. Take care, guys.